Good Monday morning, everybody. Where we left off on Friday was in discussion of image receptor systems and the historical contributions of image receptor systems to the image itself. And that's where we're going to pick up today. Um, so, um, just for historical perspective, I want to explain how it is that KVP and mass controlled contrast and density in a film screen world, and why it is that we still say that KVP controls contrast, mass controls density, and why there's sometimes different terminology that are synonymous with contrast and density in a digital world. So it helps to explain that through the context of the H&D curve, which we've talked about. And the H&D curve is still something that we use to identify characteristics of an imaging system, contrast and speed, as we were talking about on Friday. So traditional speed, speed in context of any image receptor system is its sensitivity to exposure. And in film, that's exposure and processing, because processing has a lot to do with contrast and density as well. But the way screens worked was that the remnant beam would come through the patient and interact on the screens, and the screens themselves would absorb some x-rays, and in absorption of those x-rays through basically photoelectric interaction, they the electrons would be ejected from the phosphors that made up the active layer of the screen. So the electrons would be ejected, and then they would slip back into their shell, and that loss of energy or loss of electron and the reestablishment of that electron would cause the screens to glow. And that was affected by the phosphors themselves and the atomic number of the phosphors. The more electrons there were available to be ejected, the more of a glow that you could get off of the screen. But it came with a point of diminishing returns. We had two different types of screens that we used primarily. One was calcium tungstate, and really kind of the limiting factor in calcium tungstate was the tungstate itself. What I mean by that is we've talked extensively about the inner shell binding energy of the electrons in a tungsten atom, and our X-ray photon, in order to remove that electron, has to be 69.5 kVp or above. If you think about the Brim spectrum and where the average energy of any X-ray beam lies in the Brim spectrum, that's around 1/3. So even if you're shooting an X-ray beam with 110 kVp or 100 kVp, let's say, the average energy is only going to be about 33 kVp. So the average X-ray photon would not eject the inner shell electron from the tungstate portion of a calcium tungstate atom in a screen. So the entire electron, or all the electron shells, could not be ejected by the average energy of a normal X-ray beam. So they developed some different types of screens, and they were called rare earth. And rare earth screens were a collection of three different types of phosphors, all of which had a high enough atomic number to make them useful, but a low enough atomic number and inner shell binding energy that the average X-ray beam energy could eject the inner shell electron. So those two basic types of phosphors. Because of the availability of the inner shell electrons in a rare earth, the rare earth phosphors tended to be of higher speed than the calcium tungstate. So screen speed was affected by the type of phosphors, but it was also influenced by KVP. And what I mean by that is if you shot all of your X-rays with 40 KVP, first off, you wouldn't have nearly the penetration, but at 40 kVp, your average beam energy is only going to be somewhere around 13 kVp. So even if you were using rare earth phosphors, your kVp, your average energy would be low enough that you wouldn't get the maximum ejection and replacement of electrons in the screens, so your screens would slow down. As a result, the higher the kVp, the faster the screens tended to be. So in addition to screen speed, we also had film speed. And the film speed was affected by the crystals. This is a lattice of silver. So what we had is silver halide crystals, and as far as the film speed goes, what we were really looking at there was the law of averages. So the crystals were very, very small, and again, exposure through X-ray to the crystals required photoelectric interaction, but they were also sensitive to light. And what you had in the silver halide is if you had a very large crystal, more interactions could take place on that crystal and cause a blackening of the crystal. So if you think of silver, your grandmother's true silverware, if it goes unpolished for an extended period of time, it'll actually turn black. It tarnishes. That's really what happened in films. Is the film basically underwent that oxidization that silver undergoes whenever it's exposed to oxygen and light. It turned black. So it's sensitive to both radiation and light, but there was another phenomenon that also affected screen speed, and that was spectral matching. Rare earth screens had to be matched with film that was sensitive to rare earth light. So the rare earth light actually glowed green, as opposed to calcium tungstate glows blue. So you had to have the right film with the right screens. You could put a calcium tungstate sensitive film inside of a rare earth screen, and you would get an X-ray. But the calcium tungstate film would only recognize the blue light that is coming off of the the rare earth screens. Rare earth glows green, which is blue and yellow, so all of the yellow light that is in that green would be wasted, and then the calcium tungstate film would only recognize the blue in the greens. So all of that affected speed. So how we measured screen film speed was again the study of the blackening after exposure and processing, and it was a measure of optical density. So again, the three portions of the H&D curve, and we talked about this on Friday, was the shoulder, the straight line portion, and the toe portion. The toe portion being where we get to a threshold exposure where useful densities would eventually be recorded. So the toe portion was X-ray exposure that was too low to be useful. The shoulder portion was X-ray exposure that was too high to be useful. So the straight line portion represented the useful densities. All densities were read in logarithmic exposure. So what that means is that X-ray film could record up to 10,000 different density levels, but to record each one of those density levels was just too cumbersome. So whenever you see a density of 4.0, what that means is that the 4.0 is logarithmic exposure, or a number based on logarithmic exposure, and it is representative of an image that's so dark that only 1 out of every 10,000 light photons would go through it. So if you happen to have a scientific calculator and you type in 10,000 and then you hit log, what you're going to get is 4. So basically logarithmic exposure is a small number representative of a very large number. And it's basically count the zeros. 10,000 has 4 zeros. So 4.0 represents 10,000. 3.0 represents 1,000. 2.0, 100. And 1.0 would be 10. So that's the density axis, the vertical axis. So what we read off the characteristic curve, or the H&D curve, the D log E curve, all mean the same thing, is a measure of speed, contrast, latitude, and we could identify processing issues and reciprocity failure. So speed, we talked about that on Friday, is a specific point on the H&D curve, and that point is 1.0 plus base plus fog. Base plus fog being base density, which is a blue tint that I was talking about on Friday, and the fog that's inherent in putting the emulsion or the active layer of the film onto that base. So it's always there. So 1.0 plus base plus fog is a speed. So when comparing two H&D curves, the one that's closest to the vertical axis at 1.0 plus base plus fog is your faster film. Contrast is just a measure of response to exposure. So if it takes a little bit of exposure, that's the horizontal axis, a little bit of exposure to go from light to dark, then you're talking about a high contrast image. So visually what we're looking at is a verticality of the curve, of the straight line portion. If the straight line portion is very vertical, you look at a high contrast. If it's very horizontal, then you're looking at low contrast. Remembering that contrast and latitude are inversely proportional. If you're looking at a high contrast curve, that would be one that's very vertical. That's going to be low latitude, as opposed to one that's very horizontal, that's low contrast. That's high latitude. Processing issues, in a lot of cases, that's why we would do a sensitometric study, is to identify processing issues. So our processing chemistry would get exhausted over time. In the process of processing an image, what we would do is load a film into a automatic processor that would run it through a set of rollers, and those rollers would dip the film into a processing solution that would remove unexposed silver halide crystals, and then it will run through a fixer. The development solution loosened up the emulsion. The fixer re-hardened it. Then it went through a wash cycle and a dry cycle, and then you got your finished product. So if our processor solution got exhausted, if too much silver halide was present in the processing solution, it would become less effective, and we would lose speed, and we would also lose contrast. Also, if we had some of the processor solution spill over into the fixer, we were okay. But if we had fixer spill over into the processor solution, then we would also lose both speed and contrast. Now, reciprocity failure, we could also assess if we had our chemistry was good, our developer temperature was good, our drying cycle was good, and our exposure was good, but we suddenly lost density from one day to another, then we've got a problem inside of our machine, and that would manifest itself as reciprocity failure. So again, speed is responsive of image receptor to exposure. Fast speed image receptors create more density than slow speed. So if you shot an image on a 400 speed versus a 200 speed, then you would have more density on the 400 speed than what you would have on the 200 speed. And that is because fast screens glow brighter because of the phosphors are closer together and possibly of a different phosphor type. But it also depended on films and the processing. And fast films have thicker emulsion layers with larger silver halide crystals. So we have more silver, and the silver halide crystals are much larger, and so they interact more with both the X-rays and the light. So you've looked at the characteristic curve, so I'm not going to spend any time on that. Optical density. We used to just use optical density to describe image receptor exposure. Optical density was synonymous with image receptor exposure. If you had too much density, then automatically you had too much exposure. With digital processing, that's really not the way optical density or image receptor exposure manifests itself as optical density anymore. Your computer algorithm controls your optical density much more so than your exposure, unless your exposure is either so high that you flood your phosphors and your computer can't make sense of it, or your exposure is so low that you starve your image receptor, and likewise your image receptor can't figure out what you've done. Then unless you're in those two extremes, then your computer algorithm is going to control your density, and therefore optical density is now image receptor exposure. So anytime I use the word optical density, be thinking image receptor exposure. Anytime I mention image receptor exposure, we'll go back to optical density. But optical density is the overall blackening of the image. So if you have an image that's very dense, then you have a very dark image. It's controlled again by the computer algorithm, which is in turn controlled by how much radiation strikes the image receptor. Since that quantity is controlled by your mass, then also be thinking of optical density and image receptor exposure in terms of mass exposure. So what we use to control optical density and image receptor exposure is your mass. KVP can control it, but KVP again controls the differential absorption inside of the patient. As KVP goes up, we get more penetration and less absorption. So it can change the imaging characteristics of your X-ray beam as well. So we don't say KVP controls image receptor exposure because we should not be using KVP to control image receptor exposure. We say that it affects it. Also, we don't use SID to control image receptor exposure, so SID affects it, but it doesn't control it. OID affects it, but not nearly as much as KVP or SID. The main thing that affects your image receptor exposure is KVP more than any other factor, but we control it with mass. So we got tissue thickness also affects your image receptor exposure. As tissue thickness goes up, then your image receptor exposure is going to go down. Tissue density affects it. As tissue density goes up, image receptor exposure goes down. Pathology affects it. Pathology can go in either direction. If you have an additive pathology, then your image receptor exposure goes down. If you have a destructive pathology, then your image receptor exposure goes up. Filtration affects it. Filtration, as we increase filtration, then our image receptor exposure reduces. It goes down. So if you add filtration, any kind of filtration, be it a step wedge or just more added filtration, then your image receptor exposure goes down. Filtration does not remain constant through the life of an X-ray tube. If you remember tanning, tanning is a phenomenon where primarily the filament evaporates and coats the inside of the X-ray tube, adding more inherent filtration. So over the life of the X-ray tube, your image receptor exposure will decrease if your machine is not adjusted to account for the added filtration. Every year, at least once a year, a biomed technician will adjust the X-ray tube to make sure that the output remains the same through the added filtration. And then grid use will also affect your image receptor exposure because you're adding some sort of very heavy metal absorber into your remnant beam. Your image receptor exposure goes down. So through all of those, in order to maintain image receptor exposure, you have to do something. If you want to change the imaging characteristics of your X-ray beam with KVP, if you want to increase your KVP to reduce your contrast, as KVP goes up, we get a wider grayscale, a higher latitude and lower contrast. So if you wanted to reduce your contrast by increasing your KVP, but your density you wanted to remain the same, then you would increase your KVP and decrease your mass. As you change from 40 to 72 inches, because of the divergence of the central ray, you're going to have to increase your mass. As you increase your OID, because the air gap and some of the scatter radiation created inside of the patient misses the image receptor, then we're going to have to increase our mass. As tissue thickness increases, then because of the increased absorption inside of the patient, we're going to have to increase mass. As tissue density increases, tissue density, depending on, again, what's causing the tissue density, we may have to increase KVP, but most of the time we can increase mass. Pathology, if we have an additive condition, sometimes it's appropriate to increase KVP, but most of the time we can increase mass. As filtration increases, we increase mass. We introduce grids, we have to increase mass. So, intro into technique and how it relates to exposure. We just kind of talked about some of that. KVP is directly related, but it's exponentially proportional, and we talked about that in the last section. What that means is as KVP increases, your exposure increases as well. It goes in the same direction, so it's directly related, but it's exponentially proportional. That's why whenever we increase KVP, if we want to maintain the same image receptor exposure, if we increase KVP by 15%, we have to reduce mass by a factor of 2. Or if we want to double our exposure just using KVP, we increase KVP by 15%. So 15% equals a doubling of exposure, whereas with MA or time, with mass, our exposure is direct in every aspect of the word. So we increase MA, we increase our exposure. So if we double our MA, we're using the same time, but we double our MA from 100 to 200, then it exactly doubles our exposure. Same thing holds true with mass, or with time. If we double our time, then we exactly double our exposure. So KVP changes without changing mass. It increases X-ray production exponentially. It increases emission from the X-ray tube exponentially. That increases patient exposure dramatically while increasing penetration. Now, that bears a little bit of explanation. We tend to say that high KVP techniques are they are a lower dose for the patient. But if the only thing that you change is KVP, if let's say you shoot a chest X-ray with 100 KVP at a set mass, if you change your KVP to 115, then you're going to double the exposure to the image receptor. Your patient exposure is going to go up as well, very drastically. It might not go up by double, but it's going to go up pretty dramatically. So the high KVP techniques being safer for the patient comes with the understanding that you're going to reduce the mass. So just KVP changes without changing mass will increase patient exposure pretty dramatically. So with the increase in production and the increase in emission and the increase in penetration as well as the exposure, it's going to increase the number of photons in the remnant beam, which is going to increase your image receptor exposure very dramatically. So it's an exponential increase in image receptor exposure. The results on the image are that really in a diagnostic or in a digital world, you're not going to see much except for a change in your index number. Some of your index numbers, some of your manufacturers have the index number increase with increased exposure. I think most of the ones you're using decrease with increased image receptor exposure. So what you in most cases, what you're going to see is your index number go down. So the index number will indicate that you've got an overexposure by a factor of 2. Again, we're talking about a 15% change in KVP, and with a 15% change in KVP, you get a doubling of image receptor exposure. So KVP changes with changing mass increase X-ray production exponentially, and they necessitate a change in mass to maintain exposure. So if we increase KVP and we reduce mass, our coloration on this slide is not all that good. Let me add some color. See if that helps. That didn't help a bit, did it? Okay. Back it back up. I'll highlight it, so maybe just change the color of that. Width. All right, so with increased X-ray, with increased KVP, then what we get is an increase in X-ray production, and that's exponential. So in order to maintain our image receptor exposure, we need to reduce our mass. So if we change our KVP by 15%, increase our KVP by 15%, then what we're going to have to do is reduce our mass by half. In that, we decrease patient exposure fairly dramatically while increasing penetration. So the result is the same image receptor exposure. The result on the image, well, if we were using film, then we would lose some contrast. Our image quality would actually decrease. Remembering from the last section that our image quality factors were sharpness of recorded detail. Actually, from this section as well, sharpness of recorded detail and contrast resolution. So spatial resolution, contrast resolution. If we can't resolve the contrast as well, then we lose some quality on our image. So we lose contrast with increasing KVP in screens of films. In a digital world, realistically, you're not going to see a whole lot. And let me back up. You can play with this in clinicals on slow days. I would encourage you to take something, a number of different things, and just make an X-ray of them. Not living tissue, but you can take a sharps container, a tennis shoe, a jug of barium, jug of water, water bottle, whatever, and put them all on an image receptor and shoot them all at the same time, and then adjust your KVP in both directions. Start off with maybe a technique of 60 KVP, increase to 70 KVP, shoot it, and compare the images. See if you can see any real difference in contrast or density. Do it without changing mass, do it with changing mass, and see if you can see any difference, any real difference. And then do the exact opposite. Shoot, one at 60 kVp, and then drop your kVp back to maybe 50 and see if you can see any difference. Then compare the 50 and the 70 and see if you can see any difference. It's pretty remarkable what the computer algorithm does for contrast and density. All right, so tissue and image receptor exposure. Thickness is increased patient absorption. We get an increased patient absorption with increased thickness, and that is a decrease in the amount of exposure, or how much radiation is going to pass through the patient. So the thickness and the image receptor exposure is going to be inversely proportional. Obviously some typos here. So we're going to have a decrease in image receptor interaction. So also inversely proportional. As tissue thickness goes up, image receptor exposure goes down. So mass is needed, an increase in mass is needed in order to maintain the exposure to the image receptor. Unfortunately, that drives patient dose up as well, but it is what it is. In order to maintain the image receptor exposure, we have to increase something, and that something is mass. Now, I'm going to go off script a little bit here and say that that there's a possibility in the future that we may start increasing KVP as the image receptor refinement gets better and better, and KVP less affects our contrast. It is altogether possible that we'll start increasing KVP rather than mass in order to bring the patient exposure down even lower. So tissue density and image receptor exposure. With an increase in density, we get an increase in patient absorption, and now we're really kind of talking about Zeph number. As Zeph number goes up, we get increased absorption inside of the patient because we get more photoelectric interaction. So again, we get a decrease in what comes through the patient, what transitions through the patient, and since that decreases, then we get a decrease in image receptor interaction. And again, it's inversely proportional. As density goes up, then image receptor exposure goes down. So truly atomic number, if we have a tissue type that is replaced by tissue type of higher atomic number, then we're certainly going to get an increase in patient absorption. We'll get a decrease in what's transmitted through the patient. So it's inversely proportional again. And we'll get a decrease in image receptor interaction that, again, is inversely proportional. So mass can be increased, but in this case, again, you could increase your KVP so that you can get more penetration through those tissues. You got to be careful with increasing KVP because one example that comes to mind is that if you have pleural effusion and you increase your KVP because of the pleural effusion, you've replaced air with fluid, and if you increase your KVP, then you've replaced a tissue type that doesn't create a lot of scatter radiation with a tissue type that does. So if you increase KVP, you compound that problem. You increase your KVP in the tissue type that's going to create more scatter radiation, you're going to create exponentially more scatter. So you got to be careful with increasing KVP, and as a result, most of the time we just increase our mass for tissue type, even atomic number, changes in atomic number. So other equipment and image receptor issues, if we increase our filtration, it decreases our numbers, so we have to increase our mass. If we add a grid, then it decreases numbers dramatically, and we have to increase our mass. What I mean by dramatically is we'll take a look at that in the next chapter, which is the chapter on cleaning up scatter control. And for most of your grids, what you're going to have to do is increase your mass by a factor of 3 to 6 times your mass, because of the amount of scatter and the amount of remnant beam that a grid absorbs. So if you increase your SID, then your numbers decrease exponentially. That's our inverse square law. If you go from a distance of 40 to 72 inches, then you have to increase your mass by a factor of 3.25. If you go from 40 to 80 inches, then you would have to increase your mass by a factor of 4. So the inverse square law tells us what our change in intensity is with increased SID. What I mean by that is if you change from 40 to 80 inches and you don't change anything, then the intensity striking the image receptor reduces by a factor of 4. The direct square law tells you how much of a change in technique you need because of the loss of intensity. So if you change from 40 to 80 inches, you lose intensity by a factor of 4, so you have to increase your technique by a factor of 4. You increase your mass by a factor of 4. So when we increase OID, again, we're talking about the air gap. We've increased OID. Some of the scattered photons that are created in the patient will miss the image receptor. Scatter is a density. It's a density we don't want, but it is still a density. It still goes into that count of photons that strike the image receptor. So if you have no OID and you shoot an image and you shoot with perfect density, the exposure to the image receptor is good, but your scatter is bad, and then you increase your OID so that 10% of the photons that are scattered inside of the patient miss the image receptor, then your image receptor exposure is 10% less than ideal. So what you would have to do is increase your mass. The amount of technique change that you need for an increase in OID compared to everything else is really pretty insignificant, but it does remove some photons, and therefore you have to increase your mass with the increase in OID. Okay, I'm going to take a little bit of a break, and we'll pick up with radiographic contrast after that.